Hey everyone, so in this video we're going to talk a little bit about related rates. And so here we have a problem where we have a right triangle and we're given that the angle represented by theta is increasing at 3/2 of a radian per minute. And we want to know, well, how fast is x increasing when x is equal to 5 units? So this is a related rates problem because we're trying to relate the rate at which theta is changing to the rate at which x is changing. So in order to do that, we're going to use our acronym DREDS, D-R-E-D-S, to kind of help us through the process here. So the first thing that we have to do, the first D, is draw a diagram, which nicely enough in this case is already given to us. And the next thing we would always do is to actually write out what our rates are. What rates do we know? What rates are we looking for? So in this case here, we know that theta is increasing at 3/2 of a radian per minute. So I'm going to say then that d theta dt is going to equal a positive 3/2 because it's increasing at 3/2 of a radian per minute. All right. And I can say then that what I'm looking for is dx. I know how fast theta is changing. I want to know how fast is x changing. So dx dt is the one that we're actually looking for. This is our unknown. That's what we're going to try and solve for. Alright, so now that I have my diagram, I have my rates, the next thing I need to do is to come up with an equation that kind of relates the whole diagram or all the pieces together. So in this case here, the way that theta and x and the 13 are all kind of related is through the sine ratio. I know that because it's a right triangle, I can use right triangle trig, so that means that the sine of theta is equal to the opposite side x over 13, which also means then that I can kind of manipulate that a little bit, and that x is equal to 13 times the sine of theta. Okay, so now that I have my equation, I have my rates, I have my diagram, the next step is to differentiate implicitly. So we're going to take the derivative of x equals 13 sine theta, and we're going to take the derivative with respect to time. So if I take the derivative of x, I'm going to imagine that x is some function of t, so derivative of x is just going to be 1 dx dt. So dx dt, which is really what I'm looking for, is equal to 13 times the derivative of the sine is the cosine of theta. And I have to multiply that then by use a chain rule, so times the derivative of whatever theta is. So that's going to be, again, with respect to t, so d theta dt. Okay, so I've drawn my diagram, I have my rates, I came up with an equation, and then I differentiated the equation. So the last s means to substitute and solve. So I got to remember that I don't know dx dt, right? That's the one that I'm looking for. I do know d theta dt, right? That was up there, that was 3/2. The cosine of theta is where I have to get a little bit creative. Okay, remember in this problem, we know that we're looking for the rate specifically when x is equal to 5. So if this side here is going to be 5 units, I can use Pythagorean theorem to figure out that this opposite side over here is 12. Alright, maybe I know that that's a Pythagorean triple, maybe I have to use Pythagorean theorem to find it, doesn't matter, but it's going to be a 5, 12, 13 triangle. And so that means then that the cosine, which is the adjacent over the hypotenuse, this here is going to be 12/13. So now when I go ahead and I actually try to substitute and solve and figure out what dx dt is, our equation is really just dx over dt is equal to 13 times 12/13 times d theta dt, which was 3/2. So when I multiply all that together, the 13s are just going to cancel out, and we're going to get 12 times 3/2, which really just comes out to be 18. So what this really means then is that the rate dx dt is equal to 18, which means that whatever units we were dealing in, as theta is increasing at the rate of 3/2 radians per minute, at the moment when x is 5 units, whether it was inches or centimeters was not clear, but At the moment that x is equal to 5 units, that means that x is changing at 18 units per minute. Okay, as long as theta is increasing by 3/2 of a radian per minute, the rate at which x is changing is going to constantly change, but when x is equal to 5, at that instant, it's changing by 18 units per minute. All right. I hope this helps. I'm going to upload a couple of other related rates videos with some different examples, hopefully outlining this process a little bit more. But I hope this helps, and I'll see you in the next one.